I think we can start now. So hello and welcome everybody to the first webinar within the water track. The webinar will be about flood management, and the presenter is Bernhard Tischbein, who is from the Center for Development Research at the University of Bonn. Before I will ask you to introduce yourself, Bernhard, to the participants. I would like to give you a brief overview on the participants themselves. They are mostly master students from our partner institutions in Niger, Mali, Algeria, and Germany, and have a diverse background in fields such as water management, energy, geography, biology, and related fields. Just to give you a brief background on the participants. Yeah, my function today is the moderation, but I think I will just have observing functions, and the most part of the stage is up to you. But I might want to or can help or assist you with the discussions after you have presented your presentation. So if you need some help here, I will have a look at the questions and assist you with the discussion later on. So I think that's it for now, and I would like you to introduce yourself before you start with your webinar.
Okay, we can start.
Yes.
Okay, then Anna, thank you very much for the nice introduction, and welcome to all participants to that webinar, which is on flood management. I'm a senior researcher at the Center for Development Research, and CEF in short, and CEF is partner in the RASUS project, mainly dealing with issues of water management, flood management, urban, peri-urban irrigation, groundwater conservation. So we are very much looking on the issue of how to compensate the impact from urbanization of on the water cycle. And one really hot topic is the flood management. In my presentation, I will briefly show options and the basic concept. We need then to define a design situation to come to a dimensioning of interventions. To be able to do that, we need information which we gain either from probability analysis, or as in most cases sufficient data are not available, we need hydrological modeling. Once we have established our design, we need to derive operational rules. After that, we should look on an assessment of benefits, of impact, and at the end, I just want to remind that we have to integrate all our water management interventions into an overall concept. Yeah, that is reflected by the structure. I will briefly show some, or will briefly look on some reasons for floods besides the rainfall. We will have a short view on the climate change impact. Then I will introduce to you the three-pillar concept, which is the basic concept for managing floods. And then I will focus on options to manage the floods, what is basically by reservoirs, by upgrading the hydraulic capacity of watercourses, and by bypass options. According to the three-pillar concept, there is also a need for including decentral interventions in the basin. I will not go so much for that because that is in the focus of our e-course. As I mentioned earlier, we need information to design structures to operate structures, and that is provided by probability concepts. I will give a simplified structure on the design procedure, and will try to give some examples referring to upgrading hydraulic capacity, on the way how to design reservoirs, and then at the end I will look on operational rules. This is an important issue because on the one side we need operational rules to handle our facilities, but on the other side we should be open to modify the rules as our environment, think on climate change, think on land use dynamics is changing. And as already stated, I will then add some slides showing how to do an impact assessment and how to integrate the flood management issue into overall management concepts. So my intention is basically using technical engineering thinking as a starting point to show how to derive flood management options. But I also would like to raise awareness that all these technical interventions or options need to be embedded in an economic, ecological, socio-political concept. So my starting point is technical, but really be aware that that needs to be embedded in overall concepts. Yeah, some examples on floods. Here is the big flood in the Indus River basin in 2010. We have floods in urban areas. For example, the Greater Accra region is very much endangered by floods from small basins which react very quick and endanger people. Also in Germany, we experienced floods in 2002 and 2013, which were caused by rainfall intensities which we never before observed. They reached 250, 300 millimeter per day. So there is an impact by climate change. Let's have a look on some reasons for floods besides the rainfall. That's very much obvious. One reason is, this is an example from the Danube River. We simply leave too limited space for the river. We are using too much here the floodplain for agriculture, for settlements, and there is not enough space for the rivers. Land use is an important issue. If we seal here by settlements or by traffic infrastructure part of the basin, that will then enhance the surface runoff, which is driving the flood. And what the river is doing, that becomes very much, this is a small river in central Germany. What the river is doing, he is taking back the floodplain. So what we took away from him, he is taking back in the flood events. This is an example from highly industrialized region in Ludwigshafen, and one can see we made the river straight, and this is then enhancing the peak flow, and in addition then sharpening our situation. Now a few words on climate change. Surely there is an increased variability of the water cycle. We have more extreme discharge, peak discharge in flood events. That's a bit difficult to prove, because simply our time series on rainfall, on discharge are too short, but all our physical knowledge indicates in that direction. The generation of rainfall is a complicated process, but here this graph one can this graph should make us concerned. We have an exponential relationship between the temperature and the water or the saturation of water vapor in the air. So if we move to a higher temperature and then cool down the air for a specific unit, we release much more water than at a lower temperature level, and this is an indication that rainfall intensity is increasing due to climate change, and that is then enhancing the surface runoff. As I said, the statistical proof is a bit difficult because simply our time series are too short. But there are some examples. This is a case study from the Danube River with the peak discharge per year. And what colleagues did here is they split the time series from 1926 to 1995 in two parts. This is an earlier part, assuming there is not yet an influence of climate change. And here in the later part, the assumption is there's already climate change. I will show you later that we measure basically the magnitude of a flood by its probability or by its recurrence interval. And what is visible here is there is a shift in the relation between the magnitude of the flood and the probability. For example, in the period without impact of climate change, recurrence interval of 100 years, which we basically use for conceiving flood management, is linked to a peak discharge of 263 cubic meter per second. And in the second part of the time series, assuming that there is a impact of climate change, with the same recurrence interval, we have a much higher peak discharge. So there is a shift in the probability. Or looking the other way around, if we conceive our flood management facilities on a recurrence interval of 100 years, then we have protection in the earlier period up to a discharge of 263 cubic meter. And in the time series with impact of climate change, this peak discharge has a recurrence interval of 5 years. So there is a clear increase in the flood risk. You could now question these numbers. There might be other influences besides climate change. We have here one peak which is dominating the statistics, but there is a lot of indication that we have a shift in the probability or in the relation between magnitude and probability. One further issue is, besides climate change, besides change in land use, by making our rivers more straight. This is an example from the upper Rhine Valley. Here in the historical period, there was a big floodplain, there were meanders, and what we did is we made it straight, and the consequence is that the peak flow is, or the peak of a hydrograph is moving much more quick than before, and adding up much more disadvantages with the hydrographs coming from the smaller tributaries. In the past time, the peaks from the tributaries came early, and the peak from the River Rhine came later, so there was not much adding up. Now, by making the peak in the River Rhine much smaller, it's coinciding with the peaks from the tributaries, and this is increasing the overall peak. So what we have to consider is we have the impact of climate change, we have the impact of land use, and we have the impact of reconstructing our rivers. And what is also an alarming thing is, I don't want to go here for the details, but the impact is, or the impacts from these three drivers, they are adding up. Land use change towards more settlements, more sealed area is increasing the surface runoff. Climate change leading to higher rainfall intensity is also increasing the surface runoff. So this is adding up, and reconstructing our rivers, reducing the floodplains is also leading to a quicker reaction of the basins. So all these three drivers go in the same direction, and so the impact is adding up. Okay, now I will come to the issue of how to manage now the floods. Maybe one sentence. You read very often flood protection, but for me that is a bit misleading term, because we cannot protect against floods. We can protect only up to a specific level. So I think it's better to use a term like flood management, because we have to live with the situation that there might be cases where our management cannot completely handle the discharge, and then we have to think about additional measures. Okay, what is the guiding principle? We contrast a design hydrograph, which is linked to a specific probability, and we have a discharge capacity of our river. So the two options we have to intervene is either we reduce the hydrograph by, for example, reservoirs, or we raise the hydraulic capacity of the rivers. So these are the two basic fields of intervention. This is very much technical thinking, so we have to broaden a bit our view, and here the three-pillar concept is a concept which helps in that respect. That means we need measures, what they name precaution measures. We have to integrate spatial planning. We need special kind of buildings on pillars. We need to train the people, make them aware of the risk, and have a training on how to handle it. Then the second pillar is the technical intervention, basically by raising hydraulic capacity of the rivers, by reservoirs, and by bypass options. That will be then later in the focus of my presentation. Third pillar is to enhance the water storage or the retention of basin level. That means to go for land use which is lowering the surface runoff. Special kind of land use, or for example, a practical thing is to in the agricultural fields do the plowing not in the slope direction but rectangular to it. We have to break sealed areas in urban settings, what is possible by increasing the infiltration, and we have to much better manage our floodplains. So these are the basic pillars, and I will go in the following a bit for these technical measures. What we need, or what is the starting point for any intervention? We need a design hydrograph which has a specific probability. Ideally, that is measured, but in most cases, our monitoring periods are too short, so we have to include modeling. The next step is is then to compare the design hydrograph here in blue with the hydraulic capacity of our river downstream. Let's assume the hydraulic capacity of the river is 100 cubic meter per second. Then we have a flood situation during that period simply because the hydrograph is higher than the capacity of the river. Now, what is now the basic concept of flood management by reservoirs? We store the water or the discharge exceeding the hydraulic capacity of the river in our reservoir and release it later. So what we are doing is we make of that non-managed hydrograph, we make an hydrograph like that, which is cutting at the hydraulic capacity of the river. This part of the water we store in the reservoir and release it later when discharge is low. That is the basic concept of using reservoirs for flood management. Okay, we have to be aware that all these numbers have a special tolerance due to our measurements, to the models we imply. We need to consider a reserve, and we need to be ready to adapt our strategies. Yeah, this is just a view on a reservoir. We have the basic components, the dam, we have the operational outlet, and we have an emergency spillway. In most cases, we speak about multi-purpose reservoirs. There are examples for reservoirs only for flood management, but once you build a reservoir, you think about multi-purpose use. For example, if you look on the storage or on the layers in the storage, we have the dead storage, which is the storage below the operational outlet that will be sooner or later be sedimented. Then we have the live storage, which could be for storing water for irrigation, for drinking water, for industry. And then we have the storage for flood management. And above that is the freeboard. The freeboard and the level we need for the emergency spillway. Here a hand-drawn graph by Professor Bogardi, one of the most competent hydrologists in Germany. So the emergency spillway has the function to protect the building. So we design our storage for all the purposes, and there might be now, or we design it on a, let's say, on a hydrograph of a recurrence interval of 100 years. But there might be now a stronger flood with a higher recurrence interval, and in that case, the reservoir would be completely filled, and still water is coming in and would then overtop the dam, and that could then destroy the dam and would create a wave from that dam break, which is much more damaging than in a situation there would be no reservoir. So we need an emergency spillway, which is just discharging the water in a safe way once the reservoir is completely filled. and that the recurrence interval of that emergency spillway is 1 magnitude higher than for the volume for flood management. Basically, we design flood management measures on a recurrence interval of 100 years. What is a probability of 0.001? And the spillway, the design on a recurrence interval of 500 to 1,000 years. That is just now a number. We don't have time series which really would allow to estimate such a recurrence interval. But the important issue is here for the emergency spillway, we have a recurrence interval 1 magnitude higher. Because if that is not sufficiently working, then we risk the break of our dam. And important message here is, even if we go 1 magnitude higher, there might be a flood event which is even exceeding that. So there is a risk. There is a residual risk, and we need to be aware of that. That means we can use the reservoir to gain some time, which might be used to evacuate people in case of a flood which is even higher than that. So important message here is we have the different levels of probability or recurrence interval, and still there is a risk which remains. So the next issue is, or the next option is on reconstructing rivers. That means by raising hydraulic capacity. Here in that case, we take the required discharge, which is the peak of the hydrograph, and make the capacity a bit higher than the required. Here is this is the continuity equation. This is the Manning approach, and that enables us to establish a relationship between the capacity, discharge capacity, and parameters of the longitudinal section, cross section, and of the material. I will come back to that later in a case study. But important message here is, when going for reconstruction option, we raise the hydraulic capacity of our river in a way that it is same or better, a bit higher than the peak of the hydrograph for a given probability. In our case, the recurrence interval of 100 years. Third option is then the bypass option. For example, if we are in a city, there might be not enough space to raise the hydraulic capacity, so one can then construct a bypass river around, which needs the capacity given here. Here we have an option to combine different purposes of our rivers. One can also use that bypass river for upgrading the ecological situation of the landscape, because here the rivers, creeks, in that case the bypass rivers, they are lifelines in the landscapes. They could be migration path. And we can also combine here that aquatic ecosystem to a terrestrial ecosystem. So this just as an example that we can also combine different purposes, and there is also space for compromising. For example, if we need to protect a city or infrastructure here by a flood wall, we still can give the river a bit space so that he can develop a meandering lineation which is ecologically much more valuable than a straight line. Okay, these were the options: reservoirs, upgrading hydraulic capacity, and bypass option. Now we need data for the design, and the most important thing is here we need to measure the strength or the magnitude of the hydrograph, and this we do by the probability of that peak. Here we are also at the interface between science and policy. Just to make that clear, estimating a hydrograph by statistical analysis, by hydrological modeling, this is a question of science. But fixing the level of protection, what is selecting the probability or the recurrence interval up to which protection should be sufficient, that is a political decision. So whether to take a recurrence interval of 100 years or higher, that is a political decision of the stakeholders. Yeah, as already mentioned, basically we use, in case life of population is endangered, a recurrence interval of 100 years, maybe 200 years. For the spillway, we go one magnitude higher. And if we consider very big reservoirs, for example, the Aswan Dam, then it goes even one magnitude more. So to select here the recurrence interval, that is a political issue. That is nothing of science. Just a small excursus in hydrology. We have the statistical approaches. We have the deterministic modeling approaches. Deterministic means we assume a relationship between an impact or between a cause and the impact. Rainfall comes to a basin and is causing a runoff. This is deterministic thinking. The statistical approaches, they simply try to establish a relation between the magnitude of a flood and its probability, not looking on why or when this is happening. Just looking what is the relation between the magnitude here of the flood and its probability. Okay, this I will skip. The hydrological models we need in some cases because we don't have the data on or long enough time series on the discharge. In many cases, we only have the rainfall, so we often are in a situation where we have to estimate or we have to establish a frequency relationship of the rainfall inserted as an input in a hydrological model, and then estimating the hydrograph. That is a bit risky approach because there is not only the impact of rainfall but also in the basin. But in some cases we simply do not have the data, so we have to go that hydrological modeling. But in general, we do a probability assessment, which is basically doing the following. We have given a record of measurements on the discharge. Okay, often that record is not long enough. And what we need to determine is the relationship between that value, discharge, peak discharge, and the frequency and probability. Instead of probability, we often use the recurrence interval. And the approach which we use is either to go for empirical probabilities and or for an extrapolation by theoretical probability functions. that is the task, and that is basically the result. We can also go for drought, but this I will not consider here. What we need to establish is the relation between the discharge, peak discharge, and its probability. Okay, as mentioned earlier, we need probabilities for the flood management facilities in the range of a recurrence interval of 100 years, and for the spillway 1 magnitude more, which is a challenging task. I think no need to go for these basic terms. You surely are familiar with that. Here again, the frequencies, the probability density function, and here this cumulative frequency or density distribution. We have to go from our sample to the population. We have different probability density functions. We have the symmetric ones. We have the left side skewed, right side skewed. Yeah, maybe becomes better clear in that graph. Here the symmetric, the normal distribution, the Gaussian distribution, the left side skewed, and the right side skewed. Here, in case of extreme rainfall, extreme floods, we usually go for the left side skewed probabilities. This is a scheme on how to do that probability assessment. We do a pre-processing of our data, plausibility, reliability, look for outliers. Then we estimate the statistical parameters, the mean, standard deviation, the skewness. We calculate the empirical frequencies. Then we select, or in most cases, empirical frequencies do not cover a period which is long enough. So we have to extrapolate, and for the extrapolation we select a theoretical distribution function. In case of floods, here the logarithmic Pearson 3 distribution is one which is often used. So we use that probability function to do an extrapolation. Then we go for a test of goodness of fit. For example, the chi-square is an often used test here. If it is acceptable, then we have succeeded to establish the relationship between discharge and probability. If not, we have to go for another probability function. Yeah, here just I will show you some examples. The empirical probabilities of frequencies are basically determined by ranking the peak discharge, then estimate the empirical probability depending on a plotting position formula. One which is often used is that Gumbel approach by here the rank m divided by n, that is the number of observations plus 1, and then one can get an empirical distribution. Okay, I will show you later the example. The theoretical distribution function here, for example, the logarithmic Pearson type 3, is using that basic equation. Don't look here for the details, but the basic equation is the X is the peak discharge, for example, with an allocated recurrence interval is estimated from the average, the standard deviation, and a factor which is specific for that type of distribution, and that depends then on the skewness and on the recurrence interval. That is the basic equation of all theoretical distribution functions. The difference is here in that factor k. That makes a difference between the functions. Okay, I will not go for that example. I will just show you the result. Here, that is an example. The blue dots represent empirical frequencies. This is covered by measurements, and here the red or pink line. This is a theoretical probability function here, in that case the Pearson type 3. And now the question is, does the theoretical function fit to our empirical values? And this we check then by an test for goodness of fit, chi-square, for example. But here it is already visible from the graph that it is more or less fitting. And once we have proof that our theoretical function is fitting in the range which is covered by measurements, we assume, but that is just an assumption, that we can use it for extrapolation. That is then the range of extrapolation based on that theoretical function. So we do not have here a better approach than assuming that if the function fits here in that range covered by measurements, would also fit in a range of a lower probability or higher recurrence interval. So we do an extrapolation. We have to be aware that we really do an extrapolation, and there is basically no alternative, because simply in that range we do not have measurements. So that is the plausible assumption is, if it fits in that range, we assume, we hope that it also fits in that range of lower probability. But we have to be aware that is an extrapolation. Okay, I will not show the test of or the goodness of fit. Basically, one is contrasting the number of events in the empirical values against the theoretical ones, and is then this comparing to a value from the chi-square distribution, which is then again depending on the level of significance on the number of parameters. So if the deviation here, that is basically a deviation between empirical and theoretical values, if the deviation is smaller than a critical value, then we assume that the theoretical probability function here, the Pearson, is acceptable. Okay, there are some buts. We have to be aware that we do an extrapolation, and the proof is not including that range for extrapolation. Second thing is, all these analyses are based on the assumption of stationarity. That means no long-term change in between the factors influencing the hydrograph and the hydrograph itself. And that is now questioned by climate change. Climate change is disturbing this stationarity. As I said, it's difficult to prove the non-stationarity. One attempt was that example from the Danube River. Okay, in some cases we can prove it. In others, our time series are simply too short. But nevertheless, given all these buts, we do not have a better approach. Yeah, and maybe one remark more. Mathematical people, they tell us, do not extrapolate more than 3 times the length of your time series. So if we estimate for designing an emergency spillway with a discharge with a probability of with a recurrence of interval of 1,000 years, that is not reality. That's just to have an reproducible algorithms to make our approaches comparable, because we do not have time series of 300 years, maximum 150. So this extrapolation up to a recurrence interval of 1,000 years should not be taken as a real extrapolation. It should be just understood as an algorithm which makes the results comparable. Yeah, I will briefly go now for some case studies. First is on raising the hydraulic capacity of watercourses. For that we need some hydraulic understanding. We need to know how to describe rivers. Basically, it's a straight line, it's a cycle, and it's a curvature. We need to describe our river in a longitudinal section, which is basically by the slope depending on the river length. And we need to describe our river in the cross section. For example, if we go for a trapezium, we have the bottom width, we have the water depth, and we have the side slope. And we also need to consider what is the material, what is the roughness. So these are the parameters to describe the river lineation, longitudinal section, and cross section. Okay, I will not go for the hydraulics. What we need for the dimensioning is the continuity equation, which tells the product of average velocity in the cross-section and cross-section area is the discharge, and that is constant in case there is no inflow or loss. Then we need an equation which describes the velocity depending on the characteristics or parameters of our river. An often used equation is the Manning approach. Yeah, no need here to look for the details. This is just geometry. Yeah, here that is the basic, or the main steps. These are the main steps in designing let's say the hydraulic upgrade of a river. The basic step is we estimate what is the discharge capacity using the continuity equation, the Manning approach, which is enable us then to describe the capacity depending on a roughness factor, on the slope, on the geometry of the cross section. This we are contrasting to the required discharge, which is the peak discharge with a given probability, 100 years, recurrence interval in general. That is the required discharge for flood management. And then the guiding idea of dimensioning is make capacity same or a bit higher than the requirement. And this is fulfilled then by the parameters here in the capacity equation. So dimensioning means to fix these parameters. Okay, I will now go for the reservoir. The reservoir is a further option to manage floods. There are a lot of reservoirs. There are natural lakes, artificial ones, subsurface storage, what is aquifer. We have the full range here, or we should use the full range of options to increase storage capacity of a basin, land use, decentral interventions, conserve floodplains, natural lakes. But in the following, to make it easy, I will have a look on a reservoir which is an artificial facility. What is given here is the operational rules. I will come later. What is given is a location for our dam and the topography. And this determines then the relationship between here the dam height, this is the dam height, and the volume of our reservoir and the surface of reservoir. This is simply a function of topography. This is nowadays taken from a digital elevation model. Here in our case, I assume a multi-purpose reservoir. One purpose is flood management. Second purpose is providing water for irrigation. And third purpose is to strengthen ecology, for example, by realizing a permanent water surface of minimum 2 hectares. So we translate the purposes in requirements. For the flood management, it is in volume. Here for flood management, we have to store that discharge exceeding the maximum discharge capacity of the river downstream. So we have to store here that volume. In the example which I showed you, it is around 150,000 cubic meter. If we go for irrigation, this is the discharge here, the red line, the discharge needed for irrigation. This is a design discharge in drought periods. So to ensure that level of water available for irrigation, we have to store the volume between the red line and the hydrograph. So we have to here in a rainy season, for example, store a volume which is big enough to fill here that gap. In our case, I estimated it for 300,000 cubic meter. And for ecological reason, we want to have a permanent water body of maximum or minimum 2,000 hectare. How is now the design process? Design means to determine the dam height. So the approach is the following. Maybe different approaches, but the one which is most plausible for me is we want to have always a water body of 2 hectares. This is the here that line is the relation between the dam height and the water surface. Here this line is the relation between the dam height and the volume. So we start with the basic requirement, always more than 2 hectares. Here these are 2 hectares. So we have to realize this dam height. This is 1 hectare, 2 hectares, and we need that dam height. Now we move from the water surface function to the volume function and add the volume needed for flood management, that is 150,000 cubic meter. And then we add the volume for providing irrigation water, what was around 300,000 cubic meter. And we end up then with that dam height, which is around 300. Okay, that's an elevation. Dam height is around 18 or 19 meter. That is the basic approach to determine or to do the dimensioning of the dam height. We still have to add, the hydraulic head of the emergency spillway. We need a freeboard as a reserve, but the basic approach is define the purposes, ecology, irrigation, flood management, translate these purposes into either a water surface in case of ecology, or in volumes in case of providing irrigation, water and flood management. And then you do the design by starting with the basic restriction, always ensuring that size of the water body, in our case 2 hectares. Then we end up looking on the height water surface line, end up here. Now we jump to the height volume line and add the volumes for flood management and irrigation. I would add them up, not use a part of the volume for irrigation for flood management, because if we add them up, we are ready to handle the worst case. And the worst case situation is, once we have filled our reservoir completely for providing water for irrigation, then the flood is coming, and then we need to have the full volume. Okay, operational rules. I will be brief here. Operational rules means we need to give to differentiate different cases to enable the people in a very quick way to handle the reservoir, because here time is really a limiting factor. And the most important parameters are what is the inflow, what is the hydraulic capacity downstream, and what is the filling degree of our reservoir. For example, if the actual discharge downstream is below the capacity the hydraulic capacity downstream, so there is no flood risk. If we have filled our volume for irrigation purpose, then no need for operation. Then the water comes in, goes out, because no flood problem, and the water for irrigation is filled. If, for example, the actual discharge going down is higher than the capacity, then we have a flood problem. If the volume for flood control is not yet filled, we use that volume. If it is already filled, we operate the spillway. So this is just a very simplified draft on how to come to operational rules. Main parameters are what is the water coming into the reservoir, what is going out, what is hydraulic capacity downstream, and what is the filling degree. That makes it then easy for the operator to manage that system under time pressure. Because if we go for small urban basins, here we speak about minutes or 5 minutes on which require decisions. For that we need rules. But here in yellow I put an part that we in case of very strong hydrographs expected, we could think about modifying our rules. For example, if we expect a flood which is much more than our design flood, which will clearly fill up our basin and might our reservoir and might even endanger the emergency spillway, then we could allow a discharge downstream which is a bit higher than the capacity. So we risk, or we allow a small flood damage just to save our reservoir. This is basically separating cases. When coming to realistic rules, then we have to consider probabilities, climatic situation, and we go for an optimization. Yeah, now coming to the end, I spoke a lot about technical interventions. I think I already also pointed out that in our e-course on hydrology, we have a lot of interventions on land use, on basin management. So to make it easy, I concentrated here on the technical measurements. So 3 concluding remarks. Whatever we are doing, we need an impact assessment. That is not only referring to flood management, but to any water management intervention, what includes 4 basic steps. We have to agree with all the stakeholders on the scope and the criteria of assessment. We need the modeling to work out interventions, to design our interventions, that is the dimensioning. We rank then the alternatives and come to a decision. That is then in most cases based on a multi-purpose or multi-dimensional decision approach. Important is not to forget that after the implementation we still have to do a monitoring, because here our assumptions, our modeling have a limited capacity, so we have to monitor whether the concepts really match the situation. Yeah, we need an understanding which is understanding the planning process not as a linear event starting here and ending there. We are in a cycle. Our environment is changing, so we are always moving in a cycle. Here, that graph I put in, this is an Egyptian king starting a break ground event in maybe 4,000 years ago for a canal. I put it here because not only for flood management, a major reason for failure of many infrastructure projects is that we are too much focused on construction. Politicians like break ground events, and we really underestimate the need for supporting the people in the operation, in the maintenance of our infrastructure. That is not only valid for flood management, but for more or less all the infrastructure construction. Yeah, one remark more. Important is really to work with all the stakeholders. Colleagues here from our department on policy, they have developed an approach which they name Follow the Innovation. And the core is, if we think about interventions in the field of management, we have to create transdisciplinary groups. We have to rank or pre-select promising options, and then we have to do a joint testing to find out whether these options have a potential for adoption. And at the end, once more the remark, any technical intervention needs to be put in a basin-wide concept. For example, if we cut here by a dam, a river, we impact the whole basin. Or if we have deforestation here in the upper part, this is changing the hydrograph in the whole river, even in the coastal region. So the consequence is we need an approach, and the guiding concept at the moment is the integrated water resources management concept, which takes into consideration the whole watershed, the whole basin, which has time horizon not only today but also for the future. And then we have a process of coordinating the management of water, land, and related resources in order to enable to maximize the resultant economic, but plus also the social welfare in an equitable way without compromising our ecosystems. That is the core of, or the guiding idea of the integrated water resources management approach. So we need to consider water quantity and quality, surface, subsurface water, all the users, not forget ecology. We need an cyclic understanding, what I just showed, of the planning process. We need impact awareness, and what is maybe most important, we need the participation of the stakeholders in order with them to judge before we realize a project, are the benefits high enough to allow some or to accept some impacts. Okay, with that I will close, and I hope I could give you some information on how to conceive interventions for flood management.
Thank you very much, Bernhard, for the presentation so far. So we now have about 20 minutes left for your questions. So if you participants have questions directly to Bernhard's webinar, please feel to either state within the chat box or raise your hand if you want to speak directly to Bernhard. So Musa is asking, what are the characteristics of a watershed, Bernhard?
Maybe I go back here to that graph on hydrological modeling. It was rather in the beginning. Okay, here. Yeah, what I wanted to point out is basically the statistical analysis should be using measured time series, but in most cases these are too short or even not available. then our approach is to use rainfall data, for which we have in most cases more longer time series. And with these rainfall data allocated to a specific probability, we go into an hydrological model, and we hope that then the probability of the simulated hydrograph is in the range of the probability level of the rainfall. But this is just a hope, because the basin, it's not only the rainfall, it's the basin and its characteristics which determine the hydrograph. That is the size, that is the form, that is the elevation, that is the land use, that is the density of the river network, that is the groundwater level. These are the soil conditions. So there are a lot of factors. Maybe if you, for example, in case of floods, the hydrograph is very much driven by the surface runoff. And then here, this is becoming important step in the modeling. That is the partitioning of the rainfall into surface runoff and infiltration. So here the characteristics which we consider is the distribution over space and time in the rainfall, and the infiltration. And the infiltration depends mainly on the soil characteristics. Sealed or not sealed, hydraulic conductivity, field capacity. So here that is very much a function of the soil and the slope. But if I understood your question correctly, factors influencing from the basin side the hydrograph, that is the size, the form, the river network, the soil, the geology, and all these factors. What is there's a question now on water quality and quantity.
Yeah, Ali asks, is it possible to control both water quality and quantity? And if so, how?
Yeah, I think that is a really wide
Yeah,
field, because you can intervene on the quantity and you can intervene on the quality. For example, if you want to increase water quality, you need purification plants. But there is a link. There's clearly a link. Once we intervene in the water quantity, we have an impact on the quality. For example, if we store water in a reservoir and release it in a drought period, we have a beneficial impact on the quality, because we dilute a concentration of parameters in the water. So there's always an interrelationship. Important issue is, or important link is also, we do not have only the purification plants. We have the self-purification of the water bodies. What is an ecosystem service? And to enable that ecosystem service, we need to provide, or we need to ensure, let's say, a minimum, an ecological or environmental minimum discharge. So you can intervene either on both, or in a single way on both, or you can try to use this linkage between quantity and quality. If you really want to quantify that, then you need not only the hydrological models, you need the metaflow models, which are also available. They are based on hydrological models, and they follow the processes of metaflow.
Thank you, Bernhard. Now Musa is asking, can you name it from a free hydrologic modeling? I'm not sure, but maybe he's referring to Ali's questions, if you can use hydrologic modeling to control both water quality and quantity, or to...
Yeah, that, can you name it?
I guess another one from back, it was from Olivia.
Maybe Musa, you can give some detail on what you mean exactly.
Not directly on plants. So can you please elaborate?
So as for me, I'm not quite sure what you are referring to.
Your biggest challenges on the matter.
In the meantime, you could also go and address Seku's question. Please, I would like to know how the rainfall runoff can affect the water ground quality.
Yeah, I see that question. Please, it would be, I would like to how the rainfall runoff can affect the water ground. What is meant by water ground quality?
Maybe Seku, you can.
Let's say if you have a rainfall runoff event, there are different phases. For example, if you are in an urban environment, the first part of the hydrograph is flushing away a lot of pollutions from the roads, from the roofs. If you are in a rural area, if the rainfall intensity or if the surface runoff becomes really significant, there might be erosion, there might be transportation of fertilizers. So there is an impact to quality. What is the difference between probability analysis and deterministic models? Okay, the Mike Shih is a deterministic model. The basic difference is deterministic modeling means you follow the chain of cause and the impact. So you have a system, what is your basin, and there is an impact like rainfall or snow melt, and then the basin is reacting. So
I believe that's the last unanswered question.
Bernhard, we can understand you not so good at the moment.
I believe they were answered by the rest of the
presentation. Possible, or?
It's better now.
Recent one, that's the one you mentioned among your stakeholders, governmental entities, major institutions, civil society, and private sector. And they ask you what is the role of the population itself in your action.
There was a question that deterministic and statistical approaches. Statistical approaches simply establish a relation between the magnitude of a flood, for example, and its probability, not caring why it is happening, when it is happening. And the deterministic approach, this tries to understand the mechanisms by which an effect like rainfall in a system is translated in a discharge. So the rainfall is coming to the basin, and the basin reacts by runoff. So there is a clear understanding of reason and impact. So one tries to model that by following the physical reality. Deterministic thinking, for example, related to that case study from before is if you want to estimate surface runoff, you contrast the rainfall intensity and the infiltration rate. Infiltration rate, the maximum amount of water the soil can absorb. So if rainfall intensity is higher than the capacity of the soil to infiltrate the water, then what should the water do? It is going into surface runoff. This is deterministic thinking. One wants to understand the mechanisms. I want to understand why something is happening, why there is, for example, surface runoff due to rainfall. That is the basic difference. Yeah, here that flood protection issue, that is a bit a discussion at the moment. In the former time, we spoke a lot of flood protection. But that term is now questioned because there might be then misunderstanding in the discussion. We have to be aware that we cannot protect against each magnitude of a flood. We design our flood protection facilities up to a specific probability. In most cases, with a recurrence interval of 100 years. As long as the events are below the magnitude corresponding with that recurrence interval, we can protect. But there might be floods which have a higher recurrence interval, a lower probability, and which are then stronger as the ones which we assumed in our design. And then we cannot protect. We can only manage. But that is a question on wording. It's, for me, the term protection is a bit misunderstanding because people might think we can protect in each and any situation. But there is a limit. And then maybe better to speak about management. Yes, then how to assess urban stormwater management with limited data. Remote sensing, can it help? Remote sensing can help here for getting a view on the land use. Depending on the size of basin, rainfall estimation by remote sensing can help, but in most cases here the urban basins are too small, they react too quick, so we need the meteor stations on the ground. But basically it can help, especially for the land use. Yeah, but otherwise in small basins we need the stations on the ground. Here's a question on, did you know the best deterministic which can be used in catchment in Africa? That is difficult to say. For me, there are basically not bad or good models. You have a situation on data availability, you have a purpose, and then you try to select a model which fits to your purpose. So, for example, if you go for flood management in a small basin, a rainfall runoff model is sufficient. If you go for, let's say, an analysis of drought periods, then you need a model which is including the groundwater issue. So I would not say there is a best. That depends on your basin, on the purpose, on the data availability. Let's say a very comprehensive model is, which I showed in one graph here, is the Mike Shee model. That is maybe the most comprehensive model. But whether it's justified to apply it in a situation, that depends on your purpose and depends on the data. So if you have limited data, it doesn't pay off to use a comprehensive model because you have a lot of work, but with a limited data set, even a good model cannot produce quality output. So that needs to be adapted. Then it's GIS. Okay, I'm not an expert on GIS. There will be a lecture by my colleague Dr. Navneet Kumar. He will surely go for that topic. But basically, you can use this geographical information systems to collect information, to pre-process information, and then also to visualize output, which is an important issue, especially when you want to enhance stakeholder participation, or if you want to approach policymaker. For example, an example is you do a statistical analysis of your flood. You have different levels of recurrence interval, and then you translate that peak discharge in a water level for a given cross section, and then you can come up with a zoning of areas flooded depending on the water level, which is depending on the probability. So it's a useful tool to visualize and pre-process data. Can you give example? Okay, groundwater quality I didn't consider here in the presentation because it is at least in the small basins, medium-sized basins, not too much important for flood. The groundwater issue becomes very much important if you go for drought analysis, because in that case is the discharge mainly comes from groundwater. If you want to use models, then go for example, the FEFlow is a model which has a metaflow component and also the ModFlow. I think the ModFlow is globally seen the most often used model. FEFlow is a model developed here in Germany, which has some strength in the algorithms which solve your physically based equations. Yeah, the FEFlow and the ModFlow. These models have they have metaflow component. They even have a heat component.
From the platform.
Thanks, Bernard. So I can now see that two persons have raised their hand. However, which question do you have?
I think
you can speak up if you want.
Webinar. And first of all, I would like to thank Craig and Amaya for the time, for giving us this presentation, and especially for being so engaging with the students. It was really a dynamic presentation.
Hava, can you hear me?
Everyone, when I say that you really got our attention with your presentation.
Maybe
so, thank you again.
Change their mind. Salimata, do you want to speak up?
Final statement for our students.
Salimata, can you hear me? Maybe they have changed their minds. Are there further questions from your side? Maybe, Bernard, we can wait a couple of minutes. Otherwise, we can clear.
give answers
So
to all
it
the
seems
questions about
that
this.
there are no further
these
questions. So it is now for
Um,
me to
we
thank
also
you,
have
Bernhard, for your
the
webinar, for your
the
presentation.
decisions and climate
And
change. And
to the
in
participants,
afternoon,
I'd
for
like to
conversation for
raise your
webinar,
attention that you can
how
ask
climate
questions as
services
well tomorrow
support
within the Q&A
integration
session. I think
management
Bernhard
in West
and
Africa.
Navneet Kumar will be present there as well to answer questions on the equals. And you might as well raise questions within the water discussion forum online. So whenever you have the questions, you can go there or use the Q&A sessions. So once again, thank you, Bernhard, and thank you all for your participation.